Good morning, everyone. I'm Diana, and I'm the Marketing Communications Manager at Norsat. On behalf of the company, I would like to thank you for joining us today in a timely presentation that will highlight some of the key challenges C-band satellite operators will face with the advent of the 5G era, and some of the mitigation strategies and immunity solutions available that will enable the rejection of these interferences. I'm delighted to introduce our presenter today, Michael Schefter, Chief Scientist at Norsat. Mr. Schefter has over 30 years of experience in satellite and system design and development from component to system level. His work experience spans a variety of industries, including VSAT, defense, military, and government satellite systems. He's responsible for leading Norsat's research and development team for all activities related to microwave components and satellite terminals. Mr. Schefter has a Master's of Science degree in Electrical Engineering and a Bachelor's of Science in Mathematics and Engineering. We'll begin with this presentation, after which we'll open the floor up for Q&A. Please use the question box in your control panel to submit your questions throughout the webinar, and we'll address them at the end. Also, a few housekeeping items. If you're currently not subscribed to our newsletter, please do so to stay updated on our latest events and webinars, news, new product launches, and company news. Now, without further ado, Michael Schefter.
Welcome and thank you for joining Norsat's webinar on preparations and mitigation strategies in the 5G era. My name is Michael Schefter. Today we're going to talk about 5G, the arrival of 5G. We'll talk about the 5G signals, the timeline, and the impact on SATCOM C-band spectrum. I have an example of a SATCOM antenna and a 5G base station, how they interact, and determining some interference levels. We'll talk about 5G interference and the impact on LMBs. Talk about some mitigation solutions, look at what sort of 5G interference immunity we can achieve, and then we have an example of a maritime system with on-demand 5G immunity. So as everyone knows, 5G is coming. Most major service providers have already started to do trials. Many satellite operators are already doing studies on the effects of the 5G systems and interference on their systems. And we know that there's hundreds of thousands of terminals that are going to be affected. It's estimated that more than 50,000 terminals in China alone, and the C-band Alliance has estimated more than 175,000 terminals will be affected. So what are these 5G signals? So the 5G signals are typically mobile signals. They're going to be operating in what was traditionally the SATCOM spectrum, 3.4 to 4.2 gigahertz. And as time goes on, they're starting to use up the lower part of the spectrum, and we expect that the spectrum will be used up to 3.9 gigahertz or even 4.0 gigahertz, depending on the country. We know that the guard bands will be small, could be as low as or as small as 20 megahertz. This means that these 5G signals could be operating up to 20 megahertz from their allocated band, band edge. We know that the 5G signals are high power. We know that the EIRPs are going to be, they could be up to 75 dBm. In practice, they will probably be less than that. 5G is designed to be efficient, so they try to use lower powers. Also, there's a certain amount of duty cycles going on, so it's unlikely it'll be that high all the time, but it could be that high. And it's to note that these signals are going to be much higher than the typical received satellite signal, which is typically minus 80 to 110 dBm. So what are these high power signals going to do to the LNB performance in the system? So the 5G signals, they're big and they are in band, and so they are going to start to overload the LNBs. They're going to cause gain compression and saturation. They're likely going to increase the noise floor and increase the noise temperature, noise figure. They will cause intermodulation products. And because they are in band, the 5G signals, they're going to go straight through the LNB. There's nothing to suppress them. And so those signals are going to show up as high power IF signals to to the input to a modem, and that's going to start to, or could degrade the modem performance. So how do the 5G base stations and the SATCOM terminals, what is their physical relationship? Typically, a 5G base station will be on the roof of a building. The SATCOM antenna is often on the ground and or on the roof of another building. The base station antennas typically have a down tilt, so they're pointing slightly down towards the earth or to the ground where the users are. The SATCOM antenna and the base station are separated by some distance. In this case, d meters in our diagram. The SATCOM antenna is pointed at the antenna, or at the satellite, I should say. It has the bore sight is pointed at the satellite, and the base station, the 5G base station, the signals, the antennas, essentially are pointed at an offset from the SATCOM bore sight. So you can think of it as signals being offset from the bore sight of the SATCOM antenna. The next slide is an example. So in this example, we make an assumption that the SATCOM terminal is pointed at a satellite as an elevation angle of about 35 degrees. The base station, the 5G base station, is offset from bore sight by about 20 degrees. So in this case, we're assuming it's offset by about 20 degrees in elevation and 20 degrees in azimuth. And the distance between the two is about 150 meters. We make an assumption that the base station EIRP is 34 dBW. And with these assumptions, we get an interference level at the input to the LNB of about minus 25 dBm. All of these are, it's all done at the far field, and it's, just assuming a single interferer. But interference or a signal of minus 25 dBm is much, much higher than the received signals, and is certainly going to cause problems for any LNB that doesn't have some sort of mitigation techniques in place. So what is this interference going to look like? And we touched briefly on it. So a typical LNB has about 60 dB of gain. We know that the output 1 dB compression point is around plus 5 to plus 10 dBm. What we will see is that these signals will start to cause compression. We start to see some compression even with signals as low as minus 60 dBm, and certainly the interfering signals will be higher than that. And typically the later RF stages in the mixer are the first components that are affected. We know that the 5G signals are going to show up at the output of the LNB. They are going to be high power. They will typically not be any higher than the output 1 dB compression point, because they can't really get much higher than that. But they will be high. We know that signals as low as minus 10 dBm at the input to a modem can start to impact the modem performance. It obviously depends on the modem, depends on the data rate, depends on the signal level of the modulated signal that you're trying to decode, but it will have an impact on the performance. Also, if there's a large difference in power between the modulated received signal and the 5G interfering signal, that can also cause an impact on the modem performance. One of the biggest problems that we see is intermodulation. The 5G signal interacts with the LO and with the in-band signals, creating a large amount of in-band modulation products. Because they're in-band, they really cannot be filtered out, and so they're bad enough that will cause severe degradation in a system. And then the other aspect that we would see is related to compression. As the signal levels increase, the front end of the LNB starts to get overloaded, and the noise figure will increase, as well as the noise floor will increase. So the following IF output spectrum is typical of an LNB without any mitigation strategies, without any filtering. We have a kind of a simulated receive signal at marker 1, sort of the center of the band, 3.95 gigahertz. You know, it's typically about minus 86 dBm, which is it's a good received signal from a satellite. And we have an interfering signal here at 3.6 gigahertz. And in this case, the interferer is at minus 34 dBm. That's marker 2. And you can see that, you know, it is starting to cause lots of intermodulation problems. Some of these intermod are actually bigger than the simulated receive signal. And so, you know, this is the type of thing that you see as the interfering signal increases in power. You know, you get more and more intermod products. So what can we do about it? So there's a number of techniques that can be used. The first one is to use an external filter, typically waveguide. Waveguide is usually low loss, provides good suppression of the interference, and you know the steepness. You know, all filters have a pass band and a stop band, and there's a sort of a transition band in between, and the steepness of that transition band is really relates to how close can a 5G signal be to your passband. And so this is related to the guard bands that we talked about. So for a signal, for a system where the guard bands are narrow, 20 megahertz, we need a filter that has very steep transition between passband and stop band. With anything that you add to the front of an LNB, there will be insertion loss, and you know that insertion loss impacts your system G over T. The second mitigation technique is to integrate a bandpass filter with the LNB. The filter suppression is not quite as good as an external filter, and the transition region is not as steep. Both of these are related to the technology that's used to do the filter. We have limited space inside an LNB. We want to keep the insertion losses low, so the filters are not quite as good as they can be if they're an external filter. And this, you know, adding a filter does impact the noise figure. So a typical LNB has a C-band LNB has a noise figure of about 0.4. When we add an integrated bandpass filter, the noise figure degrades to about 0.6, about a 0.2 dB degradation. However, this has less impact on the G over T than adding a filter, an external filter, as we'll see a bit later. So it is a viable mitigation strategy depending on your situation, and it can be less degradation to the system overall. A variation of this LNB with integrated filters to have a switchable bandpass filter. And this is very useful in cases where the 5G system is maybe not always present. So for example, a maritime system where at sea you might want to use the full spectrum because there is no 5G network, but at close to shore, there is a 5G network, and then you have to switch in some sort of filtering or mitigation to protect your system. In all likelihood, we will need a combination of external filters and LNBs with integrated filters. The LNB with integrated filter probably does not provide sufficient immunity for narrow guard bands, so it's quite possible that we will need both solutions. So external bandpass filters, they work by reducing the power of the 5G interference while passing the desired signals. As noted, the suppression or rejection in the transition band is much less than the stop band, and so the effectiveness of the filter on mitigating the 5G interference depends on how close to the passband the 5G interference is. The NORSAT standard bandpass filter designed for 5G interference has an insertion loss of about 0.5 dB, and its rejection is about 25 dB at 50 megahertz away, and around 200 megahertz, it's more than 70 dB. This is not a particularly steep transition region, it so it probably not a good candidate for situations where the guard band is very narrow. However, it does have a low insertion loss, and that insertion loss is typically a worst case seen at band edges. At the middle of the band, it's usually less than that. But the lower insertion loss means less system impact. So it's important to keep that in mind as we're looking at the whole solution. For situations where the guard band is very narrow, for example, 20 megahertz, we need a more extreme bandpass filter, something with very steep transition regions. This is a plot or a simulated response for a more extreme filter. In this case, the passband is 4 to 4.2 gigahertz, and we see that we have rejection of 60 dB at 20 megahertz away. So it's a very it is a good filter for particularly for situations where the guard band is narrow. The drawback, of course, is that to get this good rejection close to the passband is the insertion loss is increased, and so in this case the worst case insertion loss is about 1.3, and again that would be at band edges. At the band center, it's probably a third of that. It's probably 0.4, 0.5, but certainly at the band edge, it's going to be a more insertion loss. The second technique is to integrate a bandpass filter into the LNB. So before we show what that looks like, this is a block diagram or a simplified block diagram of a typical LNB, C-band or KU band. So typically you have a waveguide input, you have 3 LNAs to provide the good noise figure. You have an image reject filter, a mixer, and then on the IF you have a number of filters and gain stages. The spectrum plot that you see here is the same one that we saw before. So this is a desired signal at 3.95 gigahertz and a interfering signal at 3.6, and you see all of the spurious. So not surprising, there's no filters, there's no mitigation. The interfering signal causes all sorts of havoc with the system. So if we're going to add a bandpass filter, we have to do so to minimize the degradation in the noise figure. And so we do that by adding a bandpass filter after the second LNA. And we also add another bandpass filter, or we replace the image reject filter with a tighter bandpass filter after the third stage. So we got 2 RF filters, and then at IF we also adjust the filtering to make it a bit more narrow, so that we provides a bit more immunity at the IF side of things. What's not obvious from this diagram, though, is that we also need to update the mixer. On a typical LNB, the mixer is designed to provide low insertion loss, to provide and designed to work with lower power signals. But because the 5G signals are going to be very high power, we need to design a mixer and have a mixer that can handle higher powers without starting to create mixing products. So that is another key aspect of this, is that the mixer has to be redesigned to handle the higher powers. The spectrum output that you see here is a typical NORSAT LNB with integrated bandpass filter, very similar to the previous case. The marker 1 is kind of a simulated receive signal. Input is about -75, -76. The interfering signal is at 3.6 gigahertz, and it's at -25 dBm. And you can see that in band there's no intermod, and so we have essentially immunity from that 5G interferer. A variation of the LNB with integrated bandpass filter is a switchable bandpass filter, and this particular variant is useful in cases where you don't need mitigation, or you don't need 5G mitigation all the time. Similar set of filters to the previous case, but in this case, there's an alternate path which bypasses the filter. It certainly on the first filter, there's a through, so that there's no filtering. On the second filter, of course, we still need to have image rejection, so the instead of a straight through pass, we have an image reject filter. And then similarly at the IF, we still need to have some rejection. So we have a tight filter for the bandpass, for the 5G bandpass filter, and then more of a typical filter for the other through path. Again, the performance is very similar to the previous one that we saw, which is not surprising since the same filters are used. It's the only real difference is the additional switches that are added. The addition of the filters, both the integrated filter and the switchable filter, though, do degrade the noise figure. So despite adding them after the second LNA, there is some degradation. With the regular integrated bandpass filter, the degradation is about 0.2 dB. The additional switches add about an additional 2 dB, so we end up with about a 0.4 dB degradation overall. So we have to be careful that not all 5G mitigation LNBs are created equal. It is important that the LNB with the filter be designed purposely for the high power 5G interference. Adding IF filters, which can sometimes work for some types of interference, will not work here. Also, having a mixer that can handle the higher power signals is also very important. So these three sets of plots compare a NORSAT filter, or a NORSAT LNB with integrated filter that's designed purposely for 5G interference, and then a poorly designed LNB also advertised to provide 5G mitigation. And as you can see, even at signal levels of minus 60 dBm, the poorly designed LNB is starting to show intermod products. As you increase the interference, you get more products. And then when you hit the minus 25 dBm, not only do you have a multitude of intermod products, but also the gain has dropped about 30 dB. So it's important to get a properly designed LNB to make sure that you get the performance that you need. So how much 5G immunity can we actually get? So the following is a gain plot of a filter, a LNB with an integrated filter, and then the combination of the two. You can see that the LNB with integrated filter by itself doesn't give as much rejection, and the transition region is wide. The external bandpass filter is much better. It also has a steeper transition region, and then of course the combination of the two is better yet. The following tables sort of take the information in that chart, and I've also added the extreme bandpass filter to these tables, and kind of indicates the maximum interferer that you can apply without causing degradation. So this provides a measure of how much immunity can you obtain with the different combinations of LNBs, filters, and the different types of filters. So you can see that with a typical LNB with no filtering, either external or integrated, a signal of minus 65 will start to cause some impact on your system. And that our criteria for impact is that there would be no intermod, and that the interfering IF level is less than minus 5 dBm at the input to the modem. So you can see that in the column on the table on the left is assuming an interfering signal that's about 100 megahertz away from the passband. And you can see that with a standard filter, we can put in a signal of minus 30 and we get no impact on the system. If we put in a a filter plus the LNB with the integrated filter, we could even, get as high as 25 or 40 dBm signal input without causing any degradation. Of course, if you look at the case where the guard band is only 20 megahertz, we see that almost none of the combinations work except the case where you have an external bandpass filter with a purposely designed for small guard band, so a 20 megahertz guard band. However, each of these combinations will impact your system a little bit differently. So filters add insertion loss, LNBs with bandpass filters add or degrade noise figure, and so the combination of insertion loss and noise figure degradation does impact your system G over T, and of course then your system performance. So the following table kind of tries to summarize the degradation. So if we think of the first column here as just a standard LNB as your baseline, and then we add different combinations. So if we add a standard bandpass filter with a standard LNB, we have a change in the noise, the G over T of about 1.4 dB. Similarly, if we replace the standard LNB with an integrated bandpass filter, we end up with a 0.4 dB in G over T. The worst case occurs when we have something like the extreme bandpass filter and the LNB with a bandpass filter integrated. We have about a 4 dB degradation in G over T. That, these can be quite significant. 0.4 dB is not too bad, but 1.4 dB degradation in G over T is, it's the difference between quasi-error free at 8 PSK rate 3/5 and QPSK rate 3/4, right? So it's either you give up margin or you'll have to reduce your mod cods to reduce your traffic and be able to get some of that margin back. With a 4 dB degradation in G over T, the difference is even more. It's from the difference between 8 PSK rate 3/4 to QPSK rate 3/4. So quite a bit of difference in terms of system performance. So it's important to choose only the mitigation and the immunity technique that you need rather than trying to get the best case. So there's a trade-off between immunity and system performance, and so we need to try to find the optimum solution, which gives us the immunity we need, but the minimum system performance degradation. So as an example, we have a Maritime configuration here, which gives us immunity on demand. And so there's two ways to do this. One would be to have a single path, so it would be basically your transmit reject filter, and then have an LNB with a switchable bandpass filter. And the second option would be a more complicated option, would be to have a waveguide switch that basically has a full spectrum path, which has a transmit reject filter and a standard LNB, and then have a 5G mitigation path, which would have a combination of 5G filter plus an LNB with or without integrated bandpass filter. Of course, anything that we add to the front of an LNB is going to impact the system again. So adding waveguide and waveguide switches has a bigger impact than just having an LNB with a switchable bandpass filter. Again, this table summarizes some of the system impacts. The first two rows give the performance and the performance degradation of the single path. So first row is the transmit reject filter and a standard LNB. The second row is the similar transmit reject filter with an LNB with a switchable bandpass filter, and we see that there's a degradation of about 1.1 dB. So this is a simple case. If the next rows are the sort of the dual row or the dual path configuration. So the third row is essentially that full spectrum path, and we can see even with that, it's not as good as the standard path with just the transmit reject filter and LNB. You still have some degradation, and as we add more filters and different combinations of filters and LNBs, we get additional degradation in the G over T. So again, it's important to choose the mitigation strategy that you need, and don't try to choose one that's going to give more immunity than you need, because there will be an impact on your system performance. So that concludes the sort of the technical part of our discussion. If you want some more information, NORSAT has a number of case studies and application notes that we can find at our website, www.norsat.com. And I guess we'll open up the floor to questions. Thank you.
Thank you.
So thank you everyone for joining us. We're going to be opening the floor up for Q&A. So the first question that we have is, are multiple interference sources additive? So I think we're just waiting. Yeah.
Okay. So all of the sort of examples we used in this presentation were single source, but in reality, there will be multiple sources of 5G signals, different cell sites, different towers. They will accumulate to add additional interference. They won't add per se, so you're not going to get one signal that's twice as big as a single source, because they just don't add that way. But you will have multiple interfering signals, so the total power received by the LNB will accumulate, so it will double if they're the same signal level. They will be at different frequencies though, so you are likely to get more intermod than with the single tone that we simulated, and so the multiple sources is going to cause us even more problems than the single tones that we sort of simulated in this presentation.
Why do I need a BPF or the 3200 BPF? Can't I just use a 3120C?
So the 3120C is a NORSAT product, and it has some filtering at IF, but it is not a purpose-made LNB for high power sort of interference rejection or mitigation. So the 5G or any high powered signal is going to overload the front end of the 21 or the 3120 LNB, and then you're going to have the same problems that we just showed in the presentation with the intermod. It just does not provide that immunity at the front end. It also doesn't have a high power mixer in it, so it can't handle the higher power signals.
What are the symptoms or side effects seen at the satellite terminal receiving the 5G interference if I don't do filtering?
Okay, so we showed I guess sort of a spectrum analyzer output of kind of what happens, but from a system point of view, you're going to see an increase in the bit error rate. You might get sync losses, and if it's bad enough, you might even get a loss of lock from the modem.
What is the typical process to measure the level of interference at a terminal site?
I don't know that there is a specific process. It's hard, without having a 5G network in place to measure. It is difficult to measure. However, so what do? You need to look at the output of the LNB. So with the spectrum analyzer, look at the output of the LNB. That's going to show you the effects of any interference. but it doesn't necessarily show you the interference depending on what's there. So it is probably best to measure both at the input to the LNB, so the output, or the output of the OMT. That will show you the exact interference. Keep in mind though that these 5G signals, they are dynamic. They are constantly changing. So it might be a bit of a challenge to actually measure them exactly. There's probably some averaging that'll have to be done, and it may need some cooperation with the 5G vendor to maybe set up a test or something to see what we actually have.
What's the weight difference between the LNB plus external filter and the LNB integrated filter?
Sorry, the weight. There's no difference in weight between a regular LNB and an LNB with a integrated filter. So I forget the exact weights, but there's no difference in that weight. So the only difference is the weight of the filter. I don't have that offhand, but we can certainly look it up on one of our data sheets and get back. But it is really just the the weight of the filter. It's probably a couple 100 grams.
Assuming the filter is after the first amplifier stage, not external integrated with LNB, does a strong interferer drive the first stage LNA into a compression or intermodulation?
So what we found is that the first stage, we actually did a bunch of experiments. So the earlier you put the filter, the filter has loss, right? It's for the LNB the filter in the LNB that we're using. It's basically part of a PCB board. So it's not a low loss filter. It's several dB of loss. So if you put that filter right after the first LNA stage, your impact on your noise figure is going to be quite a bit more. The typical LNA, the FETs that we use, by the time you bias them for low noise, they're going to give you about 10 dB of gain, 10, 12 dB of gain. So putting a filter right after the first stage has too much of an impact on noise figure. Also, it doesn't seem to overload the first stage so much as it starts to overload the second and third stage. I guess you've got a little more gain before it hits those second and third stages. So the first stage isn't as affected as much, and putting a filter after the first stage affects the noise figure too much.
So the next question is, we are using 3.7 to 4.2 gigahertz BPF from Norsat. Isn't that enough to mitigate the 5G interference? If not, why?
So it really depends on how close the 5G signal is to that 3.7 lower band or lower sort of receive band, and the characteristics of the filter. So the typical sort of transmit reject filter doesn't really have very much mitigation in that area. A standard filter, the transition band might be maybe 100 megahertz wide. So within that 100 megahertz of transition band, you don't have nearly the interference rejection that you do in the rejection band. So if you get a high power signal in that transition band, it's possible that you're going to, but essentially the filter doesn't work because of the transition band. A standard filter is not really meant to filter out signals close to the pass band. They were designed for a different purpose, essentially.
Mike, I think this refers to your presentation. The question is, should the third row here be a minus 0.8 dB impact on the GT?
I'd have to check. It's possible. Maybe what I can do is get back to that one if I can. Maybe we can offer or answer that offline. I can check it and just verify numbers. It's possible. Sure. I made a mistake.
So the next question is, regarding the 1 dB compression point of the mixer, what is the ideal value for good protection?
I don't have an answer to that. Mixers, I don't have a good answer to that. The higher the better, obviously. But as the signals get higher, it starts to get closer to the nonlinear region of the mixer, and you start to get intermod. I mean, all mixers, the way they work, they're creating some intermod, right? Because that's how they work. But the higher the power, the more nonlinear it gets, and the more sort of products that you get. But I don't have a good answer to that. I mean, you need to choose them carefully and in context with the application. So we know the signals aren't going to be really big here, so it's a choice of a proper component. So unfortunately, I don't have a good answer to that.
Regarding 5G spectrum, which portion of the spectrum band is closer to C-band, user devices or base station tower?
Essentially, they use the same bandwidth, right? It's a TDD. Well, at least some of them are going to be a TDD system, so they're going to use essentially the same bandwidth. The difference is the handset is very low power relative to the base station, and so it tends to be essentially an omni antenna. It's pretty low power. The base station is high power, and it's got a directional antenna, so it's going to cause much more problems than the handsets. The handsets, of course, they are the same frequency, but they are just much lower power.
Is it necessary to use mitigation if the 5G antenna is far away from our Earth station?
You'd really have to do a bit of a test, right? Obviously, the further away the antenna is, the more propagation loss that you have between the base station and the satellite antenna. So of course, any interference will be less, and it could be tested, and you might not need it. Yeah, that's possible, especially if you're out in the country, away from cities where there's not much around. The antenna is far away. The satellite antenna's got a good look angle, so you're getting some mitigation from the antenna pattern of the satellite antenna. It may be okay. You really have to look at the specific case. I don't think you can answer that in generalities.
This also might be an offline question, but does Norsat have plans to develop a eBPF for countries that have FSS in 3.7 to 4.2 gigahertz?
So we have a couple of things. There's a range of bandpass filters, the regular bandpass filters, or the 5G bandpass filters, sort of the extreme bandpass filters, and a series of LNBs with integrated filters for anything from 3.4 up to 4 gigahertz. So different pass bands, and if there is a specific frequency that you need to look at, that's something that can be done as a customized solution. There's a certain amount of tuning that can be done on the filters. So some filters, if they're close, they can just be tuned. Same with the bandpass filter in the LND, they can be tuned somewhat as well. This is significantly different. It means a slight redesign, but that can be done. But there is the product line does cover sort of pass bands from 4 to 4.2, 3.9 to 4.2, all different things. All different bandwidths, all the way up to 4 gigahertz.
If 5G signals are dynamic and changing, do you have any recommendations to prepare your LNB for the future or make it dynamic as well?
So when I said, I guess the dynamic and changing can mean a couple different things. So when I said that, what I meant is that if a signal, a service provider has a allocated spectrum, maybe 20 megahertz or 40 megahertz of bandwidth, the signals within that spectrum are going to be constantly changing as the traffic loads are assigned, to different cells, to different users. So that was more to do with the interference. It's, on average, they're probably not going to change a lot. If you took a sort of a long-term average of those signals, it's just hard to measure on an instantaneous. So at a moment, what the signal looks like, because it is going to change. But on average, it's probably going to stay pretty constant. In terms of the allocation of spectrum, that's more of a regulatory issue. But once the regulations and once the spectrum is allocated, the amount of infrastructure that has to be put in, the investment that takes place, it kind of precludes their changing it an awful lot. It's they're going to be stuck with it for a while just because it costs so much to put in.
In most cases, when using a NORSAT 3120 LNB, will the BPF-C-5 combination provide the necessary filtering for 5G?
I guess that depends. Unfortunately, it's hard to say. So if you're working in an area where the 5G signals are far enough away from the passband, so if it's 100 megahertz away, for example, then and the bandpass filter is going to provide enough rejection in that area, then it would probably work fine. If your 5G signal is very close to your passband, say 20 megahertz away, then the standard BPF C-5 would not provide enough mitigation, and you would probably need something like the eBPF. So it depends on the situation, unfortunately.
What is the minimum distance between the Earth station and 5G antenna to use 5G mitigating filter or LNB?
Again, I don't know that I have an answer because that depends a lot on the geometry. The further away it is, the more losses that you have, so the interference is reduced. If the elevation angle of the satellite antenna is high, so 30 degrees or something like that, you're going to get a fair amount of rejection or mitigation just from the antenna patterns. Is that enough? It really depends on what does the base station antenna look like? What is it pointed kind of directly at the antenna, or is it are you just getting some side lobes off of it? It's too many variables to really say. Unfortunately, we would have to do a test, I think.
Can you please review again how I choose whether I need an external waveguide filter, LNB with integrated BPF, or both?
Okay, let me see if I can pull up my slides here again. Give me a second. So I'm hoping that you can see my screen. So it really depends on two things. It depends on the signal level. So what is the level of the interfering signal? And it depends on how close that signal is to your essentially your passband or your receive band. So if you look at a standard LNB, if you've got an interfering signal that's 100 megahertz away, actually it doesn't really matter as long as it's in the passband of the LNB. A signal level of about minus 65 dBm will cause interference, intermod, and it will affect the LNB. So that's with a standard LNB with no filtering. If you took a the same LNB and added a filter, so a standard filter, you would see about a 35 dB improvement at 100 megahertz away. But if your interfering signal was only 50 megahertz away, you might only see a 10 dB improvement with that filter. And if it was 20 megahertz away, you see almost no improvement, right? It basically doesn't filter enough. If you were to put in one of these eBPF, so the extreme BPF, you get about a 60 dB improvement at 100 megahertz away, and almost a 60 dB improvement also at 20 megahertz. So it's it really depends on your power level, right? You want to be able to drop the signal. How much signal do you have, and how close is that signal? So you really have to look at the two items, and it really will depend on the situation for each Earth station.
Can you recommend a resource to determine possible 5G carrier interfering frequencies and base station location that operate near an affected Earth station?
Not yet. Unfortunately, 5G is still pretty new in this band. Certainly, in the US, I don't think it's going to roll out en masse in these bands for another couple of years. In other parts of the world, there are certainly some allocations have already been given. There's some rollouts going on, but I don't think it's far enough along to actually do that. I don't know that the service providers have done their coverage maps yet, or if they have, I doubt they're sharing them. And it will obviously probably depend on demand and where they want to put base stations. It's likely to change as well, right? You may start with a certain number of cell sites and coverage, and you need to, as demand increases, you may make those smaller cell sites, and you might add more base stations and more antennas. So it's likely to change. At this point, I don't think there's enough information to make that assessment or to make that prediction.
Are Norsat's 5G mitigation products approved by Intelsat for use in their 5G mitigation rollout?
So we're working with so I would say not yet. We're working with most of the the big satellite companies and Earth station owners, but it's not it's not something that's been approved or certified yet.
Sometimes terrestrial interference signal, not necessarily 5G, is so strong none of the filtering techniques work. What would you suggest for this condition?
Depends where the signal is, obviously. If it's in so the filters, they obviously have a reject band. If they're not big enough, if there's not enough rejection to suppress the signal, either add a better filter, a higher order filter that provides more suppression in that area. That could work. You could use some sort of a notch filter to try to knock out specific frequencies if it's a fairly narrow frequency that's causing a problem. The LNB with an integrated filter will probably work better than a standard LNB because it handles higher power better. So if the interfering signal is still getting through and it's high enough, it's still going to cause a problem. But it does, because the mixer is a higher power mixer, because you do have some some filtering protecting the the last stage, you do get a bit better performance for higher power systems or for higher higher power signals. So that might be an option, but you'd also have to look at what is the signal. Is there a way to try to reduce it with some sort of a higher order filter or notch filter in conjunction with the the LNB with an integrated filter that is designed to work at higher powers.
Okay, and here's our last question. Do you produce 5G antennas?
No. Norsat is primarily a satellite microwave supplier, so we don't do 5G antennas.
Okay, actually, sorry, Mike, one more question. Can a strong 5G above P1 dB damage the LNB?
You know, if you put enough power into an LNB, yes, you will damage it, right? You know, the signals are unlikely to be so high. In practice, they're unlikely to be so high that you're going to damage the LNB. Far more likely that you're going to degrade your system performance, your bit error rate to such an extent that it's not going to work as a system. But to actually damage the LNB takes a fair amount of power to do that. And unless you're right beside a base station, and the base station is kind of pointed almost on bore site of your satellite antenna, it's pretty unlikely that you're going to damage the LNB, but you know, at least in a practical case.
Great, and so that's the last question. So I want to thank everyone for joining us today, and we'll be concluding our webinar. And if you have any other questions for Mike or any questions regarding our products, please contact us and a member of our team will get back to you. A recording of the webinar will be sent to you shortly, and it will also be available on our website on demand. So please feel free to share it with your colleagues. We'll also be sending out a survey, so please complete it and share with us your feedback regarding today's webinar and let us know what topics you would like us to cover in future webinars. So thank you very much, everyone, and hope you enjoy the rest of your week.